The common hypothesis among most researchers is that the momentum clarifications regarding the universe's starting points continue to be the most unmistakable understanding of its initial development. This hypothesis connects the arrangement of stars and planets, which eventually brought about existence, including people. Notwithstanding its unconventional name, the Large Bang hypothesis offers an exhaustive comprehension of what could have unfolded at the universe's commencement. Initially, the universe was held inside an unimaginably small space, much more modest than the top of a pin, and was densely loaded with particles. From this profoundly packed state, an enormous blast of energy and matter occurred, known as the huge explosion. This calamitous event, which took place billions of years ago, set off the sweeping history of the universe. However, as scientific knowledge advances, irregularities have surfaced, challenging the assumptions underlying this hypothesis. When NASA launched the James Webb Space Telescope, JWST, the largest and most advanced space observatory ever developed, specialists assumed that its data would confirm the theory of the universe's origin. Yet, within just 1 year of operation, the telescope surprised researchers with its exceptional ability to peer back into the universe's ancient past. The remarkable capabilities of the JWST have revealed galaxies so old that they challenge our current understanding of the universe's beginnings. This discovery has ignited a lively debate regarding the possible existence of matter from before the enormous detonation. A significant achievement came when cosmologist Rohan Natu, investigating data from the JWST, identified a galaxy that emerged not long after the huge explosion, marking it as the most distant galaxy observed to date. This revelation sent shockwaves through the scientific community, emphasizing the exceptional potential of the James Webb Space Telescope. The scope of the JWST's capacity to reshape our understanding of the universe is just beginning to unfold, bringing new insights into the earliest phases of the universe. This period, which loosely connects with earlier astronomical events, holds the key to unraveling the formation of the first stars and galaxies. The JWST findings have contradicted existing theories, uncovering galaxies with features that defy prior assumptions. The unexpected convergence of early galaxies has ignited an extraordinary scientific inquiry, compelling researchers to reconcile these new findings with established models. As scientists continue to explore these results, they are confronted with fundamental questions about the universe's true nature and the forces that shaped its evolution. Notwithstanding its remarkable scientific contributions, the JWST's key location, 1.5 million kilometers away from Earth, protected from interference and kept close to absolute zero by its sun shield, the size of a tennis court, provides a distinct advantage. This positioning enables the telescope to make continuous observations of the universe, free from the distortions of Earth's atmosphere. Equipped with a massive primary mirror and state-of-the-art instruments, the JWST was specifically designed to capture details about the early universe that were previously unattainable. This early cosmic time, known as the Supreme Dawn, began around 200 to 300 million years after the huge explosion, marking the formation of the first stars and galaxies. The processes behind this formation remain a central focus of research, with theories exploring the roles of dark matter, dark energy, and the interactions between gas and dust in star creation. The JWST's ability to observe galaxies from this critical period offers cosmologists a rare opportunity to test their current models of the universe. By studying these ancient galaxies, researchers can validate existing theories or uncover gaps in understanding that may lead to groundbreaking discoveries. Initially, it was expected that the JWST would detect only a few faint, small galaxies. However, its findings vastly exceeded these expectations. The first images of the distant universe captured by the telescope revealed a staggering number of galaxies of various sizes, ages, and brightness levels, far beyond what was anticipated. This unexpected surge of early galaxies has triggered a race among cosmologists to revise the records of the earliest massive systems. New discoveries are continuously emerging, leaving even the most experienced researchers in awe. After the JWST discoveries, both experts and the public have been eager to examine the advanced features of these early galaxies. Some experts have speculated that potential errors in how the telescope interprets large-scale observations could account for some of these astonishing results. However, The prevailing consensus is that these findings represent a paradigm shift in our understanding of the early universe, offering an exciting glimpse into how much more we may yet learn. The new revelations about early galaxies have raised significant questions about the nature of the universe, challenging traditional cosmological models. While some researchers are working to integrate these discoveries into existing systems, others suggest that they may indicate the emergence of a more intricate and mysterious universe than previously imagined. A crucial question that remains is how the universe we know today emerged from the chaotic conditions of its early stages. The JWST's initial discoveries could profoundly reshape our understanding of the huge explosion and provide new insights not only into distant galaxies and ancient cosmic structures, but also into the composition of our own Milky Way galaxy. As Mark McFadden, senior scientist for science and exploration at the European Space Agency, aptly stated, "You build these machines not to confirm theories but to break them. You simply have no idea how it will break." The history of the JWST traces back to 1985 when the Space Telescope Science Institute, STSI, began laying the groundwork for a successor to the Hubble Space Telescope. At that time, G. Weir, then the head of STSI, was tasked with envisioning what would follow Hubble. Despite initial skepticism, Weir and a small team began planning what would eventually become the James Webb Space Telescope. Unlike Hubble, which primarily observes visible light, the JWST was designed to observe the universe in the infrared spectrum, enabling it to peer deeper into space. This infrared capability is crucial for studying distant galaxies whose light has been stretched into the infrared range due to the universe's expansion, making them invisible to telescopes like Hubble. With its large, cold, star-like mirror, the JWST has become an invaluable tool for unlocking the mysteries of the early universe. The need for such a telescope became evident in 1995 when the Hubble Deep Field Observation revealed countless galaxies in a region of the sky previously thought to be empty. This discovery demonstrated the richness of the early universe and highlighted the need for a more powerful telescope capable of probing further into space. After decades of development and an investment of approximately $1 billion, the JWST was launched on December 25, 2021. By July 2022, it was ready to embark on its critical year of scientific observations. Programs such as the Early Release Science Programs and the General Observing Program were designed to search for early galaxies. While initial expectations were modest, the results far exceeded these projections. The JWST observations have already begun to challenge existing models of the early universe, revealing galaxies that defy conventional cosmological assumptions. These groundbreaking discoveries highlight the importance of pushing the boundaries of scientific exploration and showcase the phenomenal capabilities of cutting-edge technologies like the James Webb Space Telescope. As researchers continue analyzing the data from the JWST, new insights may emerge that further test and expand our understanding of the universe. When the first data from the JWST began to arrive, cosmologists eagerly anticipated the results. Many scientists had spent years preparing their data analysis systems for this moment. Instead of adhering to the traditional peer review process, which can take months, researchers chose to share their findings on preprint servers such as AR14, allowing for rapid collaboration before undergoing formal peer review. This approach facilitated swift feedback and discussions through online platforms, such as Twitter, where established scientists engaged in real-time discussions about the discoveries. Rohan Natu referred to this novel process as science by press release, and the resulting flood of discussion was both intense and unprecedented. However, concerns arose about the potential drawbacks of this accelerated dissemination of findings. Klaus Pontypool, a JWST project scientist at STSI, cautioned that while this rapid sharing of discoveries encouraged fast communication, it also risked overwhelming the scientific process. The swift spread of pivotal discoveries, particularly within such a groundbreaking mission, introduced new challenges to traditional scientific workflows. Regardless of the accelerated pace of data release, the general consensus among most experts remains that the current hypothesis explaining the origins of the universe continues to be fundamental for understanding its early stages. This hypothesis suggests that stars, planets, and ultimately life, including human existence, emerged as part of the universe's evolution. Despite its peculiar name, the theory of how things came to be offers a coherent explanation of the universe's earliest moments. Initially, the universe existed as an exceptionally dense point, far smaller than a pinhead, filled with tightly packed particles. From this compressed state, a massive release of matter and energy, the huge explosion unleashed forces that would shape the universe. This immense event, occurring billions of years ago, set the course for the universe's unfolding story. The common hypothesis among most researchers is that the momentum clarifications in regards to the universe's starting points keep on being the most unmistakable understanding of its initial development. This hypothesis associates the arrangement of stars and planets, which eventually brought about existence, including people. Notwithstanding its unconventional name, the Large Bang hypothesis offers an exhaustive comprehension of what could have unfolded at the universe's commencement. Initially, the universe was held inside an unimaginably small space, a lot more modest than the top of a pin, and was thickly loaded with particles. From this profoundly packed state, an enormous blast of energy and matter occurred, known as the huge explosion. This calamitous event, which occurred billions of years ago, set off the sweeping history of the universe. Anyway, as logical information advances, irregularities have surfaced, testing the presumptions hidden in this hypothesis. When NASA sent off the James Webb Space Telescope, JWST, the biggest and most developed space observatory at any point developed, specialists guessed that its information would affirm the theory of the universe's origin. Yet, within only 1 year of activity, the telescope surprised researchers with its uncommon ability to peer once again into the universe's antiquated past. The momentous capacities of the JWST have revealed cosmic systems so old that they challenge our ongoing comprehension of the universe's beginnings. This disclosure has ignited an exuberant discussion regarding the expected presence of matter from before the enormous detonation. A huge achievement came when cosmologist Rohan Natu, investigating information from the JWST, distinguished a cosmic system that emerged not long after the huge explosion, marking it as the most far-off cosmic system observed to date. This revelation sent shockwaves through mainstream researchers, accentuating the exceptional capability of the James Webb Space Telescope. The extent of the JWST's capacity to reshape how we might interpret the universe is simply beginning to unfold, carrying new bits of knowledge into the earliest phases of the universe. This period, which freely associates with earlier astronomical occasions, holds the key to unraveling the arrangement of the principal stars and universes. The JWST discoveries have gone against existing speculations, divulging universes with highlights that defy prior assumptions. The unexpected convergence of early universes has ignited an extraordinary logical request, compelling scientists to accommodate these new discoveries with established models. As researchers continue to investigate these results, they are faced with essential inquiries concerning the universe's actual nature and the forces that shaped its advancement. Beyond its noteworthy logical commitments, the JWST's key location, 1.5 million kilometers away from Earth, protected from impedance and kept close to absolute zero by its sun shield, the size of a tennis court, provides an unmistakable advantage. This positioning enables the telescope to make continuous perceptions of the universe free from the distortions of Earth's environment. Furnished with a massive essential mirror and best-in-class instruments, the JWST was explicitly designed to capture details about the early universe that were previously unattainable. This early infinite time, known as the supreme first light, began around 200 to 300 million years after